Hey everyone, I made this video for those having trouble understanding the Floyd-Warshall algorithm. I'm going to be breaking the video down into three parts: an introduction to the concept video, a theoretical step-by-step procedure using adjacency matrices, and finally a step-by-step procedure using code. Okay, so for this video I'm going to be introducing the Floyd-Warshall algorithm. I'm also going to be talking about the components used, the naming conventions, its time complexity, and I'm going to be initializing the first graph so that we can get the second video started. Okay, so first of all, the Floyd-Warshall algorithm is a shortest path algorithm. It will calculate and find the shortest path amongst these vertices here. These can be thought of as anything, cities, your Facebook friends. This is just data, but it'll find the shortest path between all of them, using any one of these as intermediate points to get to anywhere else in the graph. So that's pretty much what it is. It's a type of dynamic program because we're saving the points that we're using as intermediate points to get to anywhere else. But I'll talk about that in a little bit. Okay, so as for the components here, we have the actual data in a graph representation, and we have these two things here, which are adjacency matrices. These adjacency matrices you can think of as tools to help us visualize what the code will be doing. Okay, finally, this other component down here is just a template to help you go through the steps and not get lost. Okay. Now, as for the naming conventions, here we have a vertex and multiple vertices, all these teal color circles. That's a vertex of the graph, and there's also these edges here that connect the vertices together. Edges. This is a directed and weighted graph because these edges that I just pointed out, these lines connecting the vertices together, they're directed, as you can tell by these arrows. They're also weighted, which we can think of as costs. For example, it might cost $7 to go from 1 to 2, from city 1 to city 2. Also, since it's directed, you could only go from from city 1 to city 2, but not vice versa. That's pretty much what that naming convention there. That ties into the second part, which let me erase so you can see here. The second thing I'm going to explain is adjacency matrices and its naming conventions. So first of all, this is a 5 by 5 size adjacency matrix. That's because we have 5 vertices. And this will tie into its given time complexity. But let's go back to the naming conventions. So it's a 5 by 5 adjacency matrix, and we're calling this one here C sub 0. C because you can think of this as a cost. For example, it costs $0 to go from city 1 to city 1 because you're there already. Same thing with city 2 to city 2, city 3 to 3, 4 to 4, and 5 to 5. So that's a cost you can think of. That's why we named this adjacency matrix C. Now, as for the subscript that it has next to it, so in programming, you'll most likely be starting counting with 0. So in this case, our initialized version, we're starting with 0. By initialized, I mean we're just throwing the numbers in from the graph into the adjacency matrix. It's an initialized version. We haven't done anything to it yet. But once we start, we'll change the subscript to 1, which means we're going to be using 1 as an intermediate point to get to anywhere else. So for example, going from 1 to 1, then to 2. So 1 to 1, then to 2. This whole 1 row is going to just be directly filled in from the first or initialized version, because we're going from 1 to 1, then to 2, which is the same thing as just going from 1 to 2. But that's part of the naming convention. Whenever you're using a vertex as a possible intermediate point, we'll update here. Like 1, for example, we'll put 1 as the intermediate point. It's going to be C sub 1 when we're using vertex 1, C sub 2 with 2 up to the nth. But yeah, that's pretty much it for that. Also, part of the naming convention, this is more of a symbol, but whenever you can't get to a location directly, so let's say you want to go from 4, but you'll have to go to 2 first, then in that case, we're going to say that you can't get there directly, and it'll be an infinity symbol. But later on, the algorithm will calculate that you can go from 1 to 2, then to 4, and we'll update that as a intermediate point. So it's no longer infinity. We can go from 1 to 2, then to 4. But in the case of the initialized version, whenever you can't get somewhere directly, we'll use or you can't get somewhere at all, we'll use an infinity symbol. So infinity symbols will be used. Okay, so now part of the naming convention here is P. This P here is path. So with this P here, this is the whole dynamic programming side of it. We're saving the paths used as possible intermediate points, like I said. So this adjacency matrix will save that data. Again, the subscript down here, this is attributed to the vertex we're using as the intermediate point. Okay, so just to recap real quick again before I fill in the graph, the adjacency matrix, we have a graph here on the left side. The whole thing is a graph. We have vertices, these teal circles. We have edges, these lines here, and their weights, which is the number right next to them. We need all these things because the Floyd-Warshall algorithm will calculate based on the directions whether something's connected or not. It'll find the cheapest route depending on the weights. And obviously, you need to have the vertices themselves, or your points, or your cities, or your friends. Depending on the data. Okay. Now coming back to adjacency matrices here on the side, adjacency matrices, we have the cost adjacency matrix, which will go through the different iterations of how much it costs to go from one city to another, and then the P adjacency matrix, which will be saving any point we use as intermediate points, and it'll all be there. It might be a lot right now, but once I go through the steps, you'll see how this all kind of ties in. I just wanted to introduce some of the concepts and definitions and variables. Okay, so we'll initialize the first one. Let me just erase some of these things here. Let me just erase this stuff here. Okay, so let's use a graph. Let me erase some of this or all of it. Okay, so as I said, going from one city to itself, it's a cost of 0. It costs nothing to go from city 2 to city 2. Same thing from 3 to 3, 4 to 4, and 5 to 5. It's a gimmick. It's there. Okay. Now, we can just use the graph here on the side, this one, to fill in the adjacency matrix. Just by looking at the numbers going from one vertex to the other. So, for example, let's say we want to go from 1 to 2, which is 1 to 2. Our cost is 7. And we keep doing this over and over based on the graph. And we'll only use the graph the first time. The next times we'll be doing it based on the last adjacency matrix because it's all built on each other. Okay, so now let's say we want to go from 1 to 3. So 1 to 3. Well, that's a cost of 12. We'll put 12 right here. Let's say we want to go from 1 to 4. 1 to 4. Well, see, this is one of those vertices that's not connected directly. In this case, our initialized version will use an infinity symbol, which means they're not connected directly. But later on, we'll update that with intermediate point that we used. But we need to find the intermediate point, which is 2. It's easy for us as humans, but when we run the code, it has to go through every iteration to find that point. Okay, same thing from 1 to 5 is you can't get there directly, so we'll use an infinity symbol. Okay, from 2 to 1. Now, we'll use an infinity symbol when you can't go when there's no connection at all. Direction, in this case. We can go from 1 to 2, but we can't go from 2 to 1 unless, for example, use 3. But then that's the whole algorithm there. It'll find that 3 is a possible connection. But in this case, we'll use an infinity symbol. You cannot get there. Then, let's see, from 2 to 3. 2 to 3, you can actually get there, and that is a 4. 2 to 4, that's 2. 2 to 5, you cannot get there, so that's infinity. 3 to 1, you can get there, and that's 3. 3 to 2, you cannot get there, infinity. 3 to 4, you cannot get there as well, infinity. And 3 to 5, you can get there, and it's 19. Next, 4 to 1, you can not get there, so it's an infinity. 4 to 2, let's see, you can get there, and that's 6. 4 to 3, you can get there, and that's 1. 4 to 5, you can get there, and the cost is 5. 5 to 1, see, infinity symbol, you cannot get there directly. 5 to 2, you cannot get there directly either. 5 to 3, you cannot go back to 3, so infinity. And 5 to 4, 5 to 4 is 3. Okay, we filled it in. The first one here, initialized version. I'll erase some of this stuff here so you can see. That's what the initialized version looks like. We started filling in the adjacency matrix based on the graph. Now that we have that, we must use the previous, or in this case, the initialized version to build the next one using 1 as a possible intermediate point. But I'll be talking about that in the second part of the video. So as for now, we have our cost adjacency matrix initialized version, which is subscript 0. And we're going to update that to subscript 1, which we're going to be using 1 as a possible intermediate point to get to anywhere. And you'll start understanding what I mean by that in a little bit. Same thing with your path matrix. We'll be updating that to a 1, just to say that we're using 1. Whenever something does change, we know that we used 1 up to the end. Now, one thing I didn't cover, I actually haven't covered yet, is time complexity. And it's very important to know the time complexity. Okay, so again, this is an adjacency matrix that is a V times V sized adjacency matrix. What that means is it's a V times V, vertex times vertex size adjacency matrix. In order to calculate such a adjacency matrix, in this case 5 by 5, but V times V, it would be a time complexity of O n squared to calculate, well, a table. But we'll erase this here, scratch it out. But we have to go up to, again, how many vertices you have. So in this case, nth, or in this case, 5 vertices, but nth, it could be any amount. So in order to calculate one of these tables, it'll have a time complexity of O n squared. But in order to calculate, again, for every possible point to be an intermediate point to anywhere else, it'll be up to the nth. This means that your time complexity is O n cubed. Again, it takes O n squared to calculate a square table. Then you have to calculate up to the nth amount of intermediate points, which is another n, O n cubed. That's actually very important. So that's pretty much it. The summed up version of this whole the Floyd-Warshall algorithm and some of the components, naming conventions, time complexity, and well, the initialized version. We'll be using that for the second part of the video. Okay, bye-bye.